Welcome to this explainer. Look, if you've ever felt like geometry was just a bunch of dry, abstract rules, well, get ready. Because today we are going to completely change how you view the world around you by breaking down its fundamental architectural blueprints, lines and angles.
Right off the bat, I want you to just look around your environment for a second. Ask yourself, do you actually see the hidden mathematical structures shaping everything around you? Seriously, we often walk through our day totally blind to the fact that our physical reality is held together by some very strict, very predictable mathematical rules.
And this really goes to show that geometry isn't just some boring textbook concept. I mean, it's literally everywhere. From the railway tracks stretching outside your town, to the window frames letting light into your room, right down to the scissors sitting on your desk. Every single one of these relies on lines and angles. It's basically the operating system of our daily life.
So, here is our roadmap for today. First, the geometry building blocks. Second, when lines interact. Third, the angle spectrum. Fourth, dynamic angle duos. Fifth, transversals and parallel lines. And finally, number 6, a quick revision. Let's dive right in.
Section 1, the geometry building blocks. Okay, we have to start our journey at the micro level, with the absolute most basic Lego bricks of geometry. Because before we can build complex shapes, we really need to know what our raw materials are.
Let's start with the absolute foundation. A line is simply a straight path that stretches endlessly in both directions. It has absolutely zero starting point and zero ending point. When we talk about, say, line AB, just imagine a perfectly straight wire shooting off into the universe infinitely to your left and infinitely to your right. No boundaries whatsoever.
But let's be real, an infinite line isn't always useful when we want to build something like a window frame, right? When we trap a piece of that infinite line by giving it 2 fixed endpoints, we get a line segment. Unlike a line segment has a definite, measurable length. It stops at point A, and it firmly stops at point B.
Now, what if we kind of mash those two concepts together? Well, we get a ray. A ray has one fixed endpoint, but on the other side it extends endlessly in one direction. Think of sunlight. It's the perfect real-world analogy. The sun is the fixed starting point, and from there the light just shoots off endlessly into space.
Section 2, when lines interact. Let's see what happens when we crash these distinct lines into one another. Because one line on its own is fine, but the real magic happens when multiple lines share the exact same space.
There are 2 main ways lines can behave around each other. On one hand, we have parallel lines. These are exactly like those railway tracks we mentioned earlier. They never ever meet, no matter how infinitely far they extend. On the other hand, we have intersecting lines. These aggressively cross each other at one specific spot, which we call the point of intersection. Think of how the blades of a pair of scissors cross.
And when those intersecting lines lock together in a very specific, special way to form a perfect 90-degree corner, just like the edge of your notebook or the corner of your room, we actually give them a special name. We call them perpendicular lines. It's an intersection, sure, but a mathematically perfect square intersection.
Section 3, the angle spectrum. Now that we've bent the rules and crashed lines together, we've created the fascinating spectrum of angles. By making lines meet, we open up a whole new world of measurement.
Before we look at that spectrum, though, let's define what we're actually looking at. An angle is simply the space, or the amount of rotation, formed when 2 different rays meet at a shared, common endpoint. We call that exact endpoint the vertex, and to figure out just how wide or narrow that rotation is, we measure it in degrees. So angles are really just fractions of a full 360-degree circle, which, fun fact, is a number we actually inherited from ancient Babylonian astronomers. A 90-degree right angle takes up exactly a quarter of that spectrum. If we double that and open the angle completely flat to exactly 180 degrees, we get a straight angle, which makes up exactly half of the 360-degree circle. There are other types too, like acute angles smaller than 90, obtuse angles between 90 and 180, and reflex angles over 180, filling out the rest of the wheel.
Section 4, dynamic angle duos. Next up, we are pairing angles together to see how they dynamically interact in groups. Knowing a single angle is cool, but geometry is absolutely a team sport.
The most fundamental pair we need to look at are adjacent angles. Adjacent angles are basically next-door neighbors in geometry. For 2 angles to be adjacent, they must share 3 things: a common corner, the vertex, a common wall between them, which we call an arm, and they absolutely cannot overlap on the inside.
So the crucial takeaway here is this magic number, 180 degrees. When you have two of those adjacent, neighborly angles, and you add their measurements together, and they equal exactly 180 degrees, meaning their outer arms form a perfectly straight line, they form a highly powerful mathematical bond known as a linear pair.
Furthermore, when two straight lines intersect to form an X, they create four distinct angles. The fascinating rule here is that the angles directly across the intersection from each other, the vertically opposite angles, are equal. They mirror one another perfectly. Angle 1 will always equal angle 3, and angle 2 will always equal angle 4, every single time.
There's also a really crucial contrast here when we talk about angle sums. Complementary angles add up to exactly 90 degrees, while supplementary angles stretch out to 180. Want a quick trick to master this? C comes before S in the alphabet, right? Just like 90 comes before 180. So a 30-degree and 60-degree angle are complementary, while a 110-degree and 70-degree angle are supplementary. Simple as that.
Section 5. Transversals and parallel lines. For our final structural element, we're stepping up the complexity. We're introducing a new tool that cuts right through the chaos of multiple lines, the transversal.
A transversal is a straight line acting like a sword, slicing right through two or more other lines. And when it does this, it doesn't just create random shapes, it generates a highly organized, totally predictable system of related angle pairs.
When that transversal line cuts through lines that are specifically parallel to each other, it's like magic. Corresponding angles? Perfectly equal. Alternate interior angles? Also equal. Alternate exterior angles? Equal too. The only exception you really got to watch out for is the interior angles on the same side of the transversal. Instead of being equal, they are supplementary, meaning they add up perfectly to 180 degrees.
Section 6. Quick revision. Okay, let's take a quick breath and do a rapid-fire recap to lock all this essential geometry firmly into your memory. We have covered a lot of ground today.
To recap from the top, lines are endless in both directions, segments are trapped between two fixed points, and rays blast off from just one point. When lines interact, parallel ones never touch, while perpendicular ones form 90-degree corners. When they cross, vertically opposite angles act like perfect mirrors. Don't forget our duos. Linear pairs and supplementary angles stretch to 180 degrees, while complementary angles tuck neatly into 90 degrees. And finally, a transversal slicing through parallel lines unlocks a predictable code of equal and supplementary angles.
As we wrap up this explainer, I've got a challenge for you. Look around your room again. What is one specific geometric angle hiding in plain sight right now? Is it the 90-degree corner of your phone screen? Now ask yourself this: what would happen to your house, or the bridges you drive on every day, if those angles were off by just a single degree? It's kind of a crazy thought, right? Geometry isn't just sitting on these slides. It is quite literally the invisible force holding your reality together. Keep looking for the hidden math around you.